A beam of hydrogen molecules is directed toward a wall at an angle of 55 degrees to the normal, with the normal to the wall. Each molecule in the beam has a speed of 1 kilometer per second and a mass of 3.3 times 10 to the negative 24th grams. And the beam strikes the wall over an area of 2 square centimeters at the rate of 10 to the 23rd molecules per second. What is the beam's pressure on the wall? Alright, let's draw a picture of what's going on here. So we have a wall being struck. So this is supposed to be 3D here. So if you draw the normal to the wall, that would look like this. So that line is perpendicular to the wall. That's the normal. And then you have a beam of electrons basically striking the wall, but not striking it head on, striking it at an angle of 55 degrees with the normal. And then each molecule has a speed of 1 kilometer per second. So V equals 1 kilometer per second. I'm going to recommend some unit conversions right at the beginning. You don't have to do these right away, but really we're going to want everything in meters per second here. So this is 1,000 meters per second. The mass of each molecule is 3.3 times 10 to the negative 24th grams. So we could say that that's 3.3 times 10 to the negative 27th kilograms. Right? A kilogram is bigger than a gram, so there's going to be less of them. Right? 1,000 times less kilograms than grams, or 1,000 times more grams than kilograms because grams are smaller. The beam strikes an area of 2 square centimeters, which you have to get from centimeters to meters, you have to divide by 100, but since it's squared, you have to do that twice. So that would be 0.02, so it's 0.0002 meters squared. That's the area. And then we have this other little fact. The rate at which the molecules are hitting the wall is 10 to the 23rd molecules per second. So I'm not quite sure what to call that, but I'm just going to call it the rate for now. The rate is 10 to the 23rd molecules per second. Alright, and they want to know the beam's pressure on the wall. So let's talk about pressure. When we learned pressure, we said that its most basic formulation is that it's a force over an area. Right? And actually we know the area, so in a sense that's already handled. What's the force though? We have a velocity, a mass, and this rate. I'm not really sure how to use all that. What's the force of this collection of molecules with this velocity and this mass hitting that area at this rate? Well, another way to think about force that we also talked about earlier is that, and this kind of gets into the calculus of it a bit, it can be thought of as the change in momentum. So this P is for momentum, not pressure, per change in time. Or to be a little less calculus oriented, we could just say delta P over delta T. So what is momentum, or what's the change in momentum of a single molecule striking this wall? Well, in general, we think of momentum as P equals mv, right? And now I think we're getting warmer because we have a mass and we have a velocity for these molecules. But our situation is a little different. This is kind of general. We're not hitting the wall squarely, right? So if we define our reference system as having positive x to the right, this is our reference system, we're hitting the wall at an angle of 55 degrees to the normal. So the momentum that the molecule carries directly into the wall is actually, you can actually draw this triangle here, right? You can say that if this is a right angle and the hypotenuse has a velocity of 1,000 meters per second, we really just want the x component of that. So the velocity that's perpendicular to the wall is 1,000 cosine 55. So we have to include that in our momentum formula. So our momentum is mv cos 55. And we're not just interested in the momentum that the molecule has as it's about to hit the wall. We want to know the change in momentum over the time. So the change in momentum, if it carries mv cosine 55 going in and the collision is completely elastic, the molecule is going to hit and bounce back off with the same velocity in the other direction and the same mass. And this is a little bit of a leap here, but try to see if you can get on board with this. The change in momentum then would be 2 times mv cosine 55, because it was mv cosine 55 to the right before it hit, and then it bounced off, and it's going mv cosine 55 to the left after the fact. So the delta there, the change in momentum, is 2 mv cosine 55. And then we also know that this happens, this rate, we now know where we're going to use this. This tells us, what this delta P is telling us is the change in momentum for one molecule. But if we want to know the total change in momentum for this collection of molecules that's hitting 10 to the 23rd per second, we can multiply this by 10 to the 23rd. And this actually kills 2 birds with 1 stone, because this tells us the number of molecules. So this gets us the whole collective. And it tells us the time that it's happening in. All that's happening per second. So we now have an expression not just for delta P, but for delta P per unit time. So that's exactly what we're after here. And this is our force. And all we have to do is divide that expression by the area, force divided by area, and we'll be out of pressure. So let's do that. Let's set it all up and calculate the pressure. And we'll put in the units at the same time. Pressure equals 2 mv cos 55. So 2 times the mass, which is 3.3 times 10 to the negative 27 kilograms, times the velocity, which is 1,000 meters per second, times cos 55, times 10 to the 23rd, and that's molecules. It's per second, but I'll put the per seconds in the denominator. And then, so seconds goes down here, and we also need to divide by the area, which is 0.0002 meters squared. We could do a units check on all this too, but for right away, let's grab the calculator and plug the numbers in. So we have 2 times 3.3 times 10 to the negative 27 times 1,000 times cosine 55, make sure your calculator's in degree mode, times 10 to the 23rd divided by 0.0002, and we get pressure equals 1893. Pressure equals 1893. And let's do a units check. First of all, what unit should that be? It should be newtons per meter squared, which is pascals. But let's check. So we have kilograms meters per second. Kilograms meters. I'll do a fraction bar. We'll get everything in either the numerator or denominator. Meters per second, so we get seconds down here. Cosine 55 has no units. 10 to the 23rd molecules per second. Molecules per second. What do we want to do with molecules? Do we want to include that? I guess we'll include it for now. We may have to justify getting rid of it. Molecules per second. And we also have meters squared in the denominator. Meters squared. Sorry for the penmanship there. So kilogram meters per second, so we could take these 2 seconds and put it together, right? That's seconds squared. So if we take kilogram meters per second squared, that is a newton, and that's a meter squared. So newtons per meter squared is pascals, right? Newtons per meter squared is a pascal. So that's what we want. It's this molecules that's kind of bugging me here. That's how many molecules per second. Oh, you know what it is? If you think about 2 mv cos 55, that's the momentum per molecule. So we could say that this whole thing is the momentum per molecule. And then we multiply that by the number of molecules per second, and we could lose molecules at that point, so that it's not even here by the time we get to this point. So newtons here, meter per meter squared here, newtons per meter squared is a pascal. Pressure, final units, is in pascals.